When getting into graphics programming, we often start using the perspective projection matrix and even the view space transformation without much of an intuition about how these things work or how they accomplish what they do. And when we're curious and try to find out, we are often met with pages full of equations and symbols that make us sorry we even asked the question. Since no videos on the topic appear to be geared towards explaining the details like I'm 5, I decided it will be me who tries to release the graphics programming transformations for dummies. Now, the most obvious place to start, of course, would be the perspective projection. Then after we can cover view space or camera view. Now that might seem a bit backwards, but I think having perspective projection down first will give view space better context to grasp. For starters, I think we are shown the perspective projection matrix and all its formulas without much information on what they represent or do, so I think a good place to start is digging a bit deeper into this puzzle. Right away, we can discard these terms because for our OpenGL usage, they won't matter because we are working with a centered frustum around the camera's forward direction. So we have a symmetric frustum. Before showing how perspective projection changes things, I think it can be useful showing what the render looks like without that transformation. Here we have an array containing the vertex buffer data for our cube. Each vertex contains a 3D position followed by its color. We are working with a translated matrix to move it further along the Z direction, but currently we just have it sitting at the origin of the world space. Since we haven't defined a camera view, we are defaulting to having our eye view sitting at the origin as well, and we are looking along the negative Z direction. As you can see with our vertex shader, we aren't adding a view or perspective transformation, just rotating and translating. We'll cover clip space in more depth further into this video, but for now this demonstration we can say that our homogeneous coordinate W defines the clip condition for each vertex in our cube. Since without the perspective matrix, it is as if we are multiplying the vertex by an identity matrix that we will later shape into the actual perspective transformation that will cause W to hold the value of Z. Since we currently are working with no perspective projection, when multiplying each vertex by the perspective identity matrix and then doing the perspective division, we can see that it does absolutely nothing. In this case, W being 1 defines our clip space box to be 2 units wide and 2 units tall, centered at the origin. And since our cube didn't change from its transformation, it sits inside our clip space box being 1 unit wide and 1 unit tall, centered at the origin. I previously mentioned that our view space position is technically at the origin, and in this specific case, half of the cube is behind our view, and half of the clip space box is behind our view. Once we add perspective projection, you'll notice that the near and far planes define the valid depth range of our forward-facing view frustum, and the geometry outside either plane is clipped. Within our no perspective scenario, we can confirm our intuition about our scene by translating the cube -1.2 units in our forward direction. We should expect to start seeing the outer edges of the box being clipped by our clip space box. When translating the cube to -1.5 units, the clipping is even more obvious. My apologies for almost putting you to sleep with boring orthographic rendering, but now it's time for the main event. Perspective. I think a good place to start is analyzing what the first term in our perspective projection means and what it's attempting to accomplish. In the interest of simplicity, we won't worry about the aspect ratio, so we can consider these two terms for the frustum x width and the frustum y height to have identical formulas. So just imagine we have an 800 by 800 aspect ratio. For this example, we will say we have a near plane distance / depth along the z direction of 1. And the near plane's half width is also 1. We also have a field of view that is 90 degrees. So looking at this formula, we can start subbing things in and rearranging terms. Since our frustum is symmetric, we can sub in 1 for r, and for the other side half width, we can sub in -r, which gives us 2r. Since we know the depth of the near plane, even if we didn't have the near plane half width r, we could find it by using basic trigonometry by halving our field of view and rearranging the opposite over adjacent formula to solve for r. So now we can actually sub that into our original formula. The two ends cancel here and we are left with this formula for our perspective projection term. You'll notice this formula seems to hold information about the shape of our frustum's edge at what appears to be any depth. And that's much more apparent when the perspective division takes place because you can see the actual formula within it to find the frustum edge width that we use to find the edge of the near plane, and there's a good reason for this. So before we get into the reasons for that, I want to show what our perspective projection matrix looks like currently now. But you might still be wondering, what is this first term actually accomplishing? It's basically asking, given our field of view, how much do we need to scale our x vertex coordinates so that at whatever depth that vertex is at, its position relative to the frustum's edge maps correctly to the normalized -1 to 1 range. And it's asking the same for y as well. This normalized boundary is in the -1 to 1 range for x, y, and z. So we are mapping the frustum shape to this normalized box. To help illustrate this example, let's use another frustum diagram. Again, starting off, we'll have a near plane distance of 1, and a near plane half-width length of 1, as well as a field of view of 90 degrees. Now imagine we have a vertex at the coordinate 1 and -2 in the x and z. Let's draw a line from the coordinate to the camera and make note of where it intersects the near plane. We can see that it intersects the near plane at 1.5 units of its whole half-width length of unit 1. This intersection is referred to as the projection of the original x-coordinate on the near plane. And you'll notice that if we find the edge of the frustum at this original coordinate using the formula we previously looked at, you can see that we get an x length of 2 units. And since we know the original vertex coordinate x is 1, we can get the same result we got from analyzing the projection of x onto the near plane. Now, what happens to the scene if we were to change the field of view to 60 degrees with the same near plane distance and vertex coordinate? Right away, you'll notice that our near plane half-width length is noticeably shorter. And what do we notice about the projection of the original x-coordinate onto the near plane half-width length? Well, it no longer intersects at half of the plane's overall half-width length. It intersects much higher up compared to before. So depending on the field of view, the same x-coordinate is going to be scaled up or down and show up lower or higher up on our screen. So it changes how much of our view it is taking up. To illustrate why the perspective projection matrix uses this term to eventually get to this normalized value, it's useful to analyze all the different methods to calculating it. The first method we've shown is getting the x projection point on the near plane and finding the near plane half-width length. The second method is using the original x value, then finding the edge of that frustum at the z value depth that x coordinate is located at. But the third method is the most interesting and happens to be the method that perspective projection uses. This method involves us moving into clip space. When we have the term 1 divided by tan angle divided by 2 in our perspective projection matrix and then multiplying it by our x value, we get a clip space value. You might have noticed that with x-clip, we can't visually map it to anywhere in our diagram. We can think of it as moving to a new coordinate system that is different from view space. If you remember me mentioning that after multiplying the vertex by the perspective projection matrix, that w-clip takes on the value of z, you will immediately see the significance of that. Because once we perform the perspective division with w-clip after the perspective transformation, take a look at what happens to our x value. We achieve the same normalized value as before. So this shows us that the term 1 divided by tan angle divided by 2 in our perspective matrix is used so that we can transform into clip space and then make use of our perspective division to achieve our normalized value for x and y. You might wonder why we don't just add the -z to the perspective projection matrix and skip the perspective division, and the reason for this is that the matrix needs to be generic enough to work with every vertex you are transforming, so the z would have to be a different value for every different vertex. In part 2 of this video series, we'll cover the rest of the terms in the perspective projection matrix, as well as what they accomplish for our z values in our vertices, and how they are derived. If you got anything useful from this video and want to tune in for part 2, consider subscribing to keep up with the series. And if you made it this far, I appreciate you. Thanks.